Test. Okay. So this week we are going to talk about ER diagram. Okay. This is something that will be very useful for you. But let's have a little bit of coffee chat before we start the lecture proper. So what we have discussed so far is to create a table. So this was last week. So last week we also discussed about how to modify. This is to remove completely. This is to remove elements from the table. This is to add elements into the table. And then in the previous week we had relational algebra, which we then convert into a simple select from where. Okay, so as you probably have realized, last week I wasn't really responsive because I was involved in IOI 2020. I'm not sure if my name is there. Committees. So there's this. As you can see, I was pretty busy last week when we kind of have a discussion on the opening and closing ceremony. Okay, but the meeting is over. It's more or less quite fixed. So yeah, so I can now answer queries on cosmology. Again, so I'm sorry for that, but I should be back more full-time this week. Okay, so now what we're going to do for this week is that we're going to design, well, not just a table, we're going to design your entire database. And the idea is that you need to design it in a good way such that after the first deliverables, or actually the second deliverables, the first deliverable for your group project, after deliverables number 2, which is on week 6, after this, hopefully there's no major changes in your project and you can actually just continue on with your project as per normal. Okay, and some important questions that is this going to be relevant? Yes, because you're kind of your deliverable number 2. Okay. Right, so let me try to change that, see if I can test. I think should be, this is the maximum volume. Hopefully it's not too loud because I see on my screen it's kind of going into the red area. But if it's too loud, at least it's on my side, so you can simply just lower down your speaker. Okay. So the main thing that you need to know from this lecture is how do you design your table, your entire database, in such a way that you can ask questions from your table. Okay, you know how to ask from your table. Okay, so hopefully you are already familiar with this. At least you should know how to ask simple question using either relational algebra or the select from where. So we need to be able to design your database such that you can really ask from your table. There was this idea that I was talking about. You may probably forget this. It's called the universal relation. So later on, I'm going to show you what kind of information will be available in your universal relation if you design your database using ER diagram. Okay, so this is a rather important lecture for your project. So hopefully you follow this closely. Okay, so our model is called the entity relationship model, and we can usually represent this as a diagram called the ER diagram. So let's start with a brief overview of the ER diagram. We have attributes. Okay, so remember in our horse database, so we have an example on horses. When we were talking about horses, we were talking about what kind of information that we want to record about a horse. So we have a name, the weight, and so on. So those are called attributes, and they kind of map into the columns later on when you create a table. But here, don't think about the table first. Think about what do you want to capture, what kind of information you want to capture about an object. Now, a collection of these attributes will typically form an entities. An entity, just a single entity, is like a single horse, which is your star. I forget the weight and the length, but you have the one of the horse called star. This is an entity, and this entity has a type, and the type is horse because it's an information about a horse. So a collection of these entities is what we call an entity set. It's a set of entity satisfying common properties. In our case, they have the same attributes. Now, entities can be associated with other entities. So let's say, I think one of our examples was that horses and people. The relationship between them can be like you want to know which horses is owned by which person. Okay, so that's a relationship. The entry in a relationship set will basically store the information about which horse is related to which person. So that's the entry in the relationship set. That's one relationship. So the horse called Star might be owned by Jessica. Okay, this is one relationship. And given this relationship, you can actually add another attribute. So let's say the horse Star is owned by Jessica from which year? So let's say Jessica owns Star from 1980. So that's what you can capture in a relationship. Okay, so the collection of those relationships are what we call a relationship set. So the entities are drawn as a rectangle, relationships are drawn as a diamond, attributes are drawn as an oval. If the attributes are what we call an identity attributes, this identity attributes is basically an attribute that uniquely identify any entity within this entity set. Then you mark that with an underline. Okay. So this kind of map to the concept of your primary key. It may not be just one attribute, it can be multiple attributes. So there's a possibility that this particular people may be identified by two things: name and age. Okay, this is just an example. Obviously, you cannot just identify a person by the name and the age. But if you have multiple attributes that forms a primary key, then you have to underline all of them. So let's take a look at an actual example. This was our horse. This was our people table. And in our example, I believe we put the name. We said that the name, the eye color, and the color of the horse can uniquely identify any horse. Okay, it may not be true, but for our case, let's say it is true. So that's why we underline all the three attributes. These three attributes becomes the primary keys. For people, only the ID is the primary key. So only this. Now this brings us to a restrictions that you can only capture the primary key on the ER diagram. You cannot capture the candidate keys on an ER diagram. Okay, so that's the unfortunate side effect of this representation. And because, you know, if you put an underline, that means it's part of the primary key. Okay, so currently there's no way for you to capture candidate keys on ER diagram. So if you want to say that there are candidate keys, then you just have to spell it out as additional constraints. Okay, now an example of a relationship was this. So we say that the people here own a particular horse. So Star was owned by a person with this particular ID. So in a way, you can now see that the horse. So here we kind of exclude the attributes because we have shown you what the attributes were over here. So for simplicity, we often omit the attributes. So what you can see over here is that the entity sets form a table. Relationship set form a table. So this is another entity set. So a relationship set over here also form a table, but this particular table there is representing the relationship set will have a foreign key. So let me just mark this. So there's a foreign key from the relationship set to the entity set. Okay, because as you can see over here, the ID is actually referencing this ID. These three attributes are referencing these three attributes from the horses. Okay. If you have any other attributes, you can put it over here as a separate columns. Okay, there was a few questions. There are a few questions on the chat. So is identity attribute more of the candidate key than the primary key? Actually, the identity attribute is the primary key. We cannot represent a candidate key in ER diagram. Okay, so here's the important notes. Let me see. Yeah, so the last one over here, as you can see, we cannot represent candidate keys. So that's the unfortunate side effect. There's a few ways we can overcome this. One is that you can just write it out as a separate constraint in your report. Or you can invent new notations, but try not to invent too many new notations. And if you do invent a new notation, please give an explanation on what the notation is. But it is always best to stick with the standard notation. The other thing that you need to take note of is that relationship cannot have its own identities. This is a very common mistake. I've seen this every semester. A simple example of this is because last year I had this, I was quite angry with Luminous, and I just thought that, well, maybe I let the student create their own Luminous. So many of the ER diagram were something like this: student, and then there was a students, and then there was a module, right? The module was just the module code, and then there's a name, the module name. So if you want to know if the student enroll in a module, so student, let's say you have the metric. Everything else is kind of optional at this point. So you want a student to be able to enroll in a module, and if the student fails the module, then they need to re-enroll in the same module in a different year, in a different semester. So what many of the students actually do is that they have the year over here, which is kind of logical, and then they have the semester over here, which is also kind of logical. The thing that's not logical is the year and the semesters were identities. So when they create the table for enrolls, the identities, the primary key, were the metric, the module code, the year, and the sems. It kind of makes sense, but this is not how you design your ER, because these are invalids. You should not do this at all. This is totally wrong. Okay. One way you can do this is that, well, the modules itself can depend on the year and the sem. So these two attributes, the years and the sem, could be part of the modules instead. Of course, there's a disadvantage of that, which means that every semester you have to create new modules, which is in fact what we are doing in Luminous. Every semester we create a new entries on Luminous. So yeah, so that's basically part of the problem. Now, the other thing is that I think some of you have already asked, so this is, how do you read? How do you know the direction of relation on an ER diagram? So you can't. So in fact, if you read this particular ER diagram wrongly, you can say that the horses own people. And in fact, it can happen. So the only way we can differentiate this is if you have a write-up for your ER diagram. Okay, so for every ER diagram, for every block in the ER diagram like this, you just write an explanation. Now, the other thing that we can do, of course, is that we can have a more systematic way of reading things. So this particular example, it's more logical to read as a student's enrolled in a module rather than the module is enrolled in a student. But you can also read it as this module has the particular students enrolled. So either you describe it as a separate explanation, or we can have a convention in our module that a typical way of reading should be from left to right, or top to bottom. Okay, so try to design your ER diagram in such a way that it is more natural to read in either left to right or top to bottom. If I somehow already have my module on the right, on the left, then I may have to rename my relationship set, like has enrolled students. Okay, you can always change your table name such that it is more natural to read from left to right. Okay, or top to bottom. There's a question: is there a difference between solid lines and dotted lines? This dotted lines over here is not part of the ER diagram. This is just me saying that this particular table having a foreign key to this particular table. It's not part of the ER diagram. It's not normal. Okay? There's no dotted lines on relationships or entities. There's a question: do we still need owner relationship table if it's only one-to-one relationship? Okay, so in this semester, I will try not to use those particular terms. Okay, I will not use one-to-one, one-to-many, many-to-one, or many-to-many. The reason is because I've seen almost every semester that this leads to confusion, especially when we talk about ternary relationship. Is this ternary relationship one-to-one, one-to-many? The answer is you can't describe it that way because you have three. So you can say like one-to-one-to-one, but then you may have a confusion on which one is one, which one is many. Okay. So we have other ways to describe things, but to answer your question, you still need the owner relationship, even if it's one-to-one. So for instance, I think this one has more. You have A, you have R. So this is an abstract example. So it is a one-to-one. But there's an additional property that is implicit over here, is that A is an entity that need not even participate in this relationship. Okay, so you can have a table in A of A containing some values like 1 and 2, B containing values of 2 and 3, and yet at this particular relationship only 2 and 3 are related. 1 is not related to anything, 2 is not related to anything. Okay, so yes, you will still need the owner relationship. So when you say one-to-one here, it's not a kind of, we're talking about relationship. We're not talking about functions. If it's a one-to-one functions, then, well, everything has to be, every element, if it's a one-to-one function, every element on this particular set has to be associated with every element on this set. But this is a relationship. A relationship has different properties from functions. Okay, so you still need. Okay, so there's a question: relationship cannot have its own identity. No need to have its own identity. It will eventually have a primary key. The table corresponding to the relationship set has a primary key, and the primary key is the primary key of the entities that are being associated. You can think of it as more like restrictions of this, but this was how Peter Chen. So this is the inventor. This was how Peter Chen view an entity relationship diagram. There's another question: when do we make the relationship a separate table by itself, and when do we make it foreign key? So we will have a slide on conversion from ER diagram to SQL. So hopefully at that point it will be clearer. Okay, so we leave this particular discussion for later. Okay, so let's head to uh, archipelago. So I'm going to open the first question. So let's see if you can answer the first question. So I'm trying to make this more interactive. I'm trying to make this lecture more interactive by trying to use archipelago. See if it works. So if you try to head over to archipelago, see if you can open it and try to answer that. And do let me know in the chat if you can't answer that. Okay, it seems people are yeah, so you need to check your email, and it might be in the spam folder. Oh, okay, let me check if archipelago.rocks. Let me see if I get a request. I don't. Yeah, I didn't get the So okay, for those of you who yeah, so we have answers coming in, which is good. A Okay, so more and more are coming in. Good. And but if you see, so let me bring this. If you see the this one, you can actually answer multiple. You can answer multiple choices. It's more of a multiple selections rather than a single choice. It's more of an MRQ rather than MCQ. Okay, so let's close this one first. So it's already closed. So let me show you the question, and these are the response. So a lot of people are answering that one is correct, and 3 is correct, 2 could be correct. So this, the answer is actually 1 and 3. Okay, so the correct answer is actually 1 and 3. 2 is not actually a correct answer. Okay, so the reason why 2 is not the correct answer is because we cannot represent candidate keys. We can only represent primary keys. Since we have 2 candidate keys, so either lecture time or module name time, then we can only choose one of them as our primary key. So this is something that you need to take note of. All right, so be careful with this, because as you can see, it is something that you can easily forget. Okay, so let's recap on what we have done for this. Where's my pen? So note, only PK, no candidate keys. So if you have multiple candidate keys, then choose one. Okay, so try to be careful with that. Okay, so 2 is wrong because you cannot represent candidate keys. Okay, now we already talked about a simple entity set, a simple relationship set. We can now talk about the relationship constraints. So there are 4 kinds. There are actually only 3 kinds of arrows. If it's just a single arrow, well, if it's not even an arrow, if it's just a single line like this, we say that it's unconstrained. If it's a double line like this, it means it has a total participation. What it means is that every single entity in this entity set must be associated, must have an entry in this relationship set. But you can have more. So to give an example, let's say I have an entity called A, and let's say I have it's associated to another entity. In the relationship set, in the table rel, what I will have will be I have A, and then the second one I don't really care. I may also have A again, but this, so I can have multiple A's as long as for every element over here it has an entry in the relationship set. For a key constraint, every element here can be may not have an entry on rel, or if it has an entry on rel, it can only have at most 1. So this way is 0 or 1. Okay, so for this particular case, if you have a rel, you can have A, but the second one, a second entry like this, is wrong. Okay? There is a question, why candidate keys cannot be represented? It's because for the option 2, that's not a candidate key, that's a super key. Because you have everything. It's not the minimal, so you need to kick out one of those. And which one you choose will basically make that the remaining ones to be the primary key. Okay, there's this one. It's basically a combination of a double line and arrow that is exactly 1. Sometimes it is useful to represent it as this because, so think about it this way, right? if I have an entity A that must be related, must be in a relationship with entity B. Okay, this is a very strong constraint. Every entity in the entity sets A must be associated with an entity in the entity set B. So what does it mean? Well, why can't we just make, so if this one has an attribute A2, this one has an attribute A1, okay, so let's say A2 and A3. Why can't I just make the A to be something bigger that basically allows us to add more of this? Why can't I just, why is it not equivalent to just A having A1, A2, and A3? Okay, so why? Well, sometimes it is more useful to do this because for all we know, B can also be related to another entity sets using another relationship set. Okay, so we cannot just look at this particular ER diagram in isolation. We have to look at it in a general view. Now, there's the downside to this is that it means that if you somehow have A with a key and total participation relationship with this, and B is not related, is not associated with any other entities, then might as well just make this to be a single entity. Okay. So let me give you another common mistake that the student in the previous year make. This one is even stronger than that, but I can actually still, I can simplify this. Let's say I have users. Every users has password. Okay, a lot of students last year did this, but this is not good because password is not related to anything else, and password should actually be just an attribute of the user. So this can actually be simplified as users with a password. Okay, because every user must have a password, and in this particular case, a password is not associated with anything else. So this is common mistake, and the reason why there was so many of this problem last year was that because, well, I think it's mainly a problem every year. Part of the reason is because we want you to have 15 total entity sets plus relationship set. So to add up more entity sets and relationship set, people add this. This basically adds 2. Okay, but if you're doing this, this is bad design. You should not be doing this at all. Okay, just because you need to fill up a quota, don't just add something that is unnecessary. So try to think more about what kind of functionalities you can add to your project such that you can add something meaningful. You can add a more meaningful entities, or you can add a more meaningful relationships. Okay, now to make this relationship constraints more concrete, I do have certain examples. For unconstrained, this is an unconstrained relationship. So unconstrained. A student can participate multiple times, as you can see from here. A student may not even be enrolled in any courses, as you can see from this particular student. And similarly, for a course may have multiple students enrolled, as you can see from here, or a course may not have a student at all, like you can see from here. So that's how you can try to identify whether this particular table kind of have an unconstrained. Oh, okay. So there's a comment. You can't see the diagram. So let me just draw the diagram over here because it has more open space. So this was common mistake last year. So you have users, and then it has a relationship has and password. Okay. In this particular instance, for most of the students, the password are not related to anything else. It's not involved in any other kind of relationship with any other entities, only with the users. So in fact, it is not even supposed to be an entity at all, because think about it, you cannot have a password that does not get attached to a particular user. It should in fact be something like this. So that's the first mistake. The second mistake is, well, this one is not, it doesn't even make sense to make it into a relationship, because a password should be, so this is are actually equivalent. You should make it as an attribute. Okay. So yeah, so when you add entities and relationships into your ER diagram, you need to make sure that they are useful and they are meaningful. So the top one is not meaningful to have. It can be just represented as an attribute. Okay. Yeah. So there's another way you can represent this, which I will kind of talk about later. But let's take a look at the second kind of relationship constraint. This one is a key constraint. Okay, so the professors can supervise multiple students, or they can supervise no students at all. But a student, you can see over here, if a student is being supervised, then the student can only be supervised by exactly one professors. Okay, so this is what makes it to be a key constraint. You cannot have another arrow pointing towards somewhere. Okay, so this one is not. It's not allowed. But you can have a student not supervised at all. Let's say if the student is not doing FYP, then the student need not be supervised. So there's a key constraint. There's a, I believe this is what many of you call one-to-one, but again, we will not be using this. This is key constraint over here, and there's a key constraint over here. Yeah, that's how we will describe it. Because this kind of description will work nicely on the ternary relationship. So let's talk a little bit more about what this one means, which means that if I have a student, let's say this student, either the student is involved in the work, either the student has an entry, this is an entry in this particular table, either student has an entry or student don't have an entry at all. Okay. If student have an entry, then student must have exactly one entry. So similarly for project, either a project does not have an entry, or if a project has an entry, it must have exactly one entry within the works table. So that's what key constraint. So another way we can write this is that it is 0 up to 1, 0 up to 1. A project can only be involved in works at most one. There's an excellent question here. If password must be an attribute of user, then why horses and person is considered a relation? Because you can have a horse without person, and you can have a person without a horse. So that's why they are separate entities. But you cannot have a password without a user. There's no collection of password just floating around. Well, I mean, this is your system. You should not have a collection of passwords floating around in your database that, well, no users are using this. Okay, so that's the main difference. But those difference is because we can actually kind of map that to a particular real world object. Okay. Oh, key constraint is not. Is key constraint? This is key constraint, 0 or 1. So it's not 1 or more. So yeah. Okay, now for the total participation constraint. This is total participation. I will quite often abbreviate this to just total constraint. Because it takes too long to say total participation. Okay, so I'll just typically say total constraint. Although that's kind of a wrong thing to say, but it's just a habit of mine. Okay, so hopefully you can understand when I say total constraint. Now, in a total participation constraint, you do not have an entity that is not involved in the relationship. So there's no entity over here that does not exist within the right table. So this one is not available. Okay, there can never be such an entry. Okay, there can never be such a book. But for the author is unconstrained. Okay, another way we can write this is 0 up to n. N is arbitrary, so 0 up to n. So King here is an author, but he hasn't written any book. So there is a possibility for this because author is unconstrained, but books has a total participation constraint. So book must have an entry in the rights table. Okay, so go back to Archipelago. Let me open the second question. So try to answer the second question. This one is a line. It is a line question, so you just have to drag the line to the corresponding from the left to the right. Okay, let me give you a few moments to do this while I try to answer some questions. How about the scenario where the book has no words in it? Well, I don't really have words, but if a book has no author, I think. Well, I mean, if you talk about real world, I've never seen any book without an author. But let's say, for instance, you want to allow a book without an author, then you should not draw it this way. Okay. If you allow a book without an author, then this is wrong. But of course, what it means is also that this ER diagram is your design. You try to make it to conform to the real world as much as possible. Okay, but you can always set your own additional constraints if you want. And my constraint for this is that, well, to me, it doesn't make sense that books does not have an author. So I'm the one designing this. I'm the one who said that every book must have an author. Okay. So try to change your mindset to the one that is a designer of your database. So when you design your database, try to make it such that you are the one setting up the constraints. All right? Okay, so the answers are coming in. If you're wondering why the choices are those numbers, well, 0 is just 0. 20 comes from entity 1, 30 comes from entity 2, 50 comes from the sum of those two, 600 comes from a multiplication of those two. Okay, good. So the answers are coming in. So let's close this and let us view the response. So a lot of people say that, well, 0. So diagram 1, the minimum number of entries. Okay, so while I'm explaining this, I'm going to open the other question, which is about the maximum number. So try to answer the other one first while I'm trying to explain this. Minimum, right? For arm constraint is definitely going to be 0, because while we say that there's this relationship, it can be that no entities is related yet. So a quick example is like a student enrolls in a course. At the start of the university beginning, once you set up your database and you get your students registered to your university, you have your courses set up, no student have been enrolled into any courses yet. So that's fine. So diagram 1 is definitely the minimum is 0. For diagram 2, you need to look at this key and total participation, which indicates that every element in entity 1 must have an entry in the relationship, and they must have an entry exactly 1. So diagram 2 is actually 20. The minimum is 20. It's not 30, because after that, after the 20, you cannot have any more entries there. There's not enough entity 1 to go around. Okay, so it's a minimum. For 3, it's also 20, so many of you get it correct. For 4, it is again 0. We're talking about minimum here. Even though you kind of want to say that, well, the student, so the entity 1, if they are involved in this particular relationship, then they can only be involved exactly 1 time. But they may not be involved in the relationship. So again, this is something that you need to be careful of. So let's take a look at the maximum now. So here we are talking about maximum. So let's close this. For the maximum, it definitely cannot be 0, right? Because you can have an entry there. For diagram 1, it's actually 600. Okay, so many of you get it correct. The number of entries in the relationship set rel is definitely 600. For every entity in Ent1, you can have, it can be associated with every entities in Ent2. Okay, so diagram 1 here is 600. For diagram 2, the maximum is actually 20. Okay, and there's a reason why it's 20 is because there's not enough of entity 1 to go around. Okay, so for entity 1, it must be in the relationship at most one time. So once all 20 entities have been in a relationship, then there's no more entity 1 to go around. So the remaining 10 entities, or maybe fewer than 10, maybe more than 10 entities in N2, cannot have a partner from entity 1. And similarly over here, the entries in the entity 1 is already maxed out. It's already 20. Once 20 of them have an entry in the relationship set, then nothing else from the entity 2 can have a partner in entity 1. Okay, so this is just part of the problem. For the diagram 4, it's also 20 because again it's maximum of 1. So once all 20 entities over here, once all 20 entities in entity 1 have been in the relationship set, there's no more entity 1 to go around for entity 2 to be partner with. Okay, so this one is 600, 20, 20, 20. Okay, so that's the reason. Okay, so there's comments. Sure, I can give you more time. For the to see your attempt, I don't think I can do that because I think that's a limitation of the system. Okay. There's an interesting question. Can we generalize that as long as we have exactly one constraint, max equals to min? When you have exactly one constraint, there's another possibility, and that is the diagram is totally wrong. Okay, so let me show you what it means. Okay, so let's look at this. I'm just using this for a pet. Let's say I have E1. Oh, that. There's a relationship here, and then let's say I have this. Now, instead of having entity 1 having 20 and entity 2 having 30, if I have 20 in entity 2 and I have 30 in entity 1, this particular diagram cannot exist. Why? Well, every entity over here, so every entity in E1, so every E1 inside E1 must have a partner, right? So I must have E1, E2, where E2 is inside entity 2, but E2 can only appear once. So once all 20 of this is exhausted, I have 10 entities in E1 that does not have a partner. But entity 1 cannot have, must have a partner because of the total participation constraint. So this particular diagram where the values are 20 and 30 is totally wrong. It cannot exist. Okay? So there's another possibility, and that is that it's totally wrong. Is it possible to use cosmology? So the main problem is that the cosmology has a limited kind of survey, and I can't show you all the attempts. So the other thing that I want to show is I want to know what you don't know or what you know. Okay, so that's part of the reason why I'm using Archipelago. We have gathered a few, or at least I have gathered some knowledge about this, and that is that many of you are still not comfortable with this, with this kind of reasoning of how many number of entries. Okay, so that's part of the things that I want to know. And also for this one, I kind of know that a lot of you are still mistaking the second entry as being somewhat correct. Okay, so there's advantage of using archipelago and there's advantage of using cosmology, but for this one, at least for archipelago, I know what I want to know is what you are kind of struggling to understand from the lecture. Okay, so there's another question: why is the maximum of diagram 4 20 and not 30? For diagram 4, the entity 2 need not be, some of the entities in entity set N2 may not be in the relationship. But if they are in the relationship, they must have a partner, which is an entity in the entity set N1. But there's not enough N1 to go around because there are only 20. So, yeah. So that's the reason. If an entity can have null, you need to separate the concept of entity and relationship. And currently, when you say entity can have null, that means the attributes can be null. Yes, the attribute can be null. We don't really care about that. What we want to know is when they are involved in the relationship, do they have a partner? Okay, if they are involved in the relationship, they must have a partner. Okay, so let me summarize. Well, I thought I have a summary page, but let's look at this one first. There's another questions that I'm opening. This is the n-ary. So there's an n-ary relationship. So try to figure out this n-ary relationship. And in the meantime, I'll try to answer questions from the live stream. I thought diagram 4 is 30 because n1 can be 0. Well, n1 can be 0, but that means we're talking about minimum. So you have n1 relationship n2. Okay, we have, let's say we have e1, e2, e1 1 e1 2. They may not be in the relationship. Okay, so this entity may not be in the relationship, but that's not the maximum or the minimum. That's somewhere in the middle. When you want to talk about what is the minimum, then you can assume that if it's just this, if it's this, then you can assume that this one is not there, this one is not there, this one is not there. So the minimum is 0. But if you have this, how many entries are here? Well, this one cannot be not inside rel. E11 must be inside rel because you have the total participation constraint. Okay, so when you talk about the minimum, then you need to look at the total participation, whether there's any total participation constraint. Now, when you talk about maximum, here, if we say that, we can say that, well, let's try to make sure that everyone in entity 1 appears in the relationship. If this entity appears in the relationship, they can only appear exactly once. So, for instance, let's say I have E11 associated with E21. I cannot have this. So either one of this is wrong, because I can only, entity 1 can only be associated in the relationship exactly once. Okay, so let's say we erase this. Oh, but now E21 can also only appear exactly once. So you need to find a particular mapping such that it gives you the maximum number. Now we say that there are 20 entities here and there are 30 entities here. So once I've used up all like this, once I use up everyone in the entity 1, this particular entity does not have a partner, and it cannot have a partner. Okay? Because if it has a partner, that partner must have violated this particular constraint. So you need to be very, very careful with this. There's a question now on the impossible diagram. Well, the impossible diagram is really impossible because this is what we have. E21 can only appear in the relationship exactly once. E22 can only appear in the relationship exactly once. So who is the partner of E13? E13 cannot have a partner, but by not having a partner, it violated this particular constraint. If it has a partner, so let's say E13 is associated with E22, then E22 violates this constraint. So it's impossible. There's no way you can satisfy this. Okay? So that's why it is impossible. Okay, so yeah, so let's see the archipelago. Let's close this. So to figure out what are the constraints on this n-array relationship, we need to simply look at this. This arrow is a key constraint. Everything else, like this and this, are basically unconstraints. Okay, so a professor, you see, this is how I like to do this. So let's say I have a professor P1, and then there's an entry in the works. I have D1 and B1. Let's say there's already such an entry, P1, D1, B1. Okay, so the question is, there can be prof not working in any department or any building. Well, that means that can I have a P2 over here? So definitely I have P1, but can I have P2? Well, the answer is yes, because this is a key constraint. Okay, so the first one is correct. Can a department not having a professor and not having a building? Yes, because this is unconstrained. 3. There can be a building not in any department and not having a professor. Yes, because this is unconstrained. Okay. There can be a prof working for a department but in 2 different buildings. Okay, so this question 4, what it means is that there can be a prof working for a department but in 2 different buildings. So if I already have this, what it means is that can I have this? Is this thing allowed? But the fact that I have duplicate P1, it violates the key constraint. So this one is wrong. Okay, so 4 is incorrect. And then can there be a prof working for 2 different departments but in 1 building? So what you need to ask yourself, so this P1 working in one building, so D1 again, but in two different departments, sorry. Two different departments, but in the same building. Okay, so again, this will still violate the key constraint. Okay, so 5 is wrong. Okay, 6. Can there be a department with a prof working in two different? So yeah, so that means that it's the same prof again. The department is still the same, working in two different buildings. Okay. So the same department, the same professor, two different buildings. So again, this is not allowed. Yeah, so you can try to reason about this. For the rest, there's an implicit one. There's always an implicit one, and that is, if I have P1, D1, B1, there is no way I can have exactly the same entry. This is totally not allowed, even though both P1, all P1, B1, D1 are the same. Okay, so this one is definitely not allowed. Okay, so that's the n-ary. So let's take a look at other kinds of arity. For this one, so I'm using a terminology that is, I don't really find it in many books, but a lot of books actually say that this is unary. Okay? But this one, I'm not going to use this terminology. I'm going to call this a recursive relationship because an entity is related to itself. So I'm calling it recursive, but this is actually still binary. Binary means it's 2, unary means it's 1. Okay, so I'm still calling this a binary. This one is also binary because it's 2. This one is ternary. So the question is, so think about this for a moment. Arity can start from 0. So these are common names. There's nullary, unary, binary, ternary, and I forgot what this one. Okay, so I'm not sure what this one is. Typically, we don't go into. Typically I don't go into this many. So, what I want you to think about is there a possibility for a nullary and a unary? So far we don't have, right? Even this one is still binary. We don't call it unary. Can there be a true nullary relationship? Can there be a true unary relationship? Okay, so think about it for a moment, whether it's possible or not. You can have a discussion in the forum if you want, but we are going into something that is more relevant now. How do we draw the entity relationship diagram given a description? So this is something that is even more relevant to your project because I gave you the description of a project in this particular way. I gave a kind of a write-up on what your system would look like. So how will you try to translate that into an ER diagram. Okay? So there are ways to do this. What you need to know is you need to first categorize words over here, or words or phrase or anything over here, into entities, relationships, or attributes. Okay. There are useful guides on the book. So entities are typically things like places, items, people, or something even more abstract like events, achievements. Okay? But those are kind of objects, kind of feelings. And typically they relate to what we call as a noun. Relationships are something more towards the verbs. Okay, and attributes. Okay, my English is pretty bad, but I think it's something called adverbs or adjective. My English is pretty bad, but yeah. So it's there are things that you can look out for to kind of try to figure out if these things should be entities, should be relationship, or should be adjective. So first, well, the first thing that you can notice that like I would like my customers. So customers here is probably an entity. So you can have an entity set called customers. And you can have an entity set called books. Okay, so these are probably entity sets. Place here is not, because it's kind of place orders. So that's not exactly an entity. But place orders kind of describes a verb, right? It's an action. The customer orders books. Or I think this one is more clearly, so this one should be relationships. And now we can try to take a look at things like attributes. So when you look at the book, you can see the ISBN numbers of a book because that describes a book. In fact, ISBN is typically your primary key. And then you can have a quantity. Quantity here is going to be an attribute. Credit cards. Now credit cards is an object, so you can actually, you have a choice. You can put it as an entity, or if you feel like it's not a strong enough entity, you can say that, well, maybe it's related to the order itself. It may be an attribute on the orders, but let's say our choice here is that credit card is going to be an entity. And then you read for each book. So ISBN, we have already established that. There's title, author, price. There's two price, purchase price and sales price, and the year. So these are attributes for books. And then it says that they have records of their names and address. So these can be attributes of customers. Now there's this thing, unique customer identification number. So this should also be part of the customer attribute. Okay, so we have a lot of customer attributes. We have 3 customer attributes. We have 6 book attributes. Quantity is unlikely to be related to the books. It is most likely going to be an attribute of the orders. Again, a relationship set can have their own attributes. So a customer order a book with a certain quantity. So the quantity should be a property of the, should be an attribute of the orders instead of the books itself. So we can kind of draw this ER diagram, which will give us something like, well, we have the customers, we have books, orders, and then I can have a credit card. Okay, it can be a ternary relationship like this. For the order, we say that there is a quantity. Customer, there's a unique customer ID. There's a name. And there's the address. For the book, there's ISBN. There's author, name, year, and so on. A credit card, the attribute wasn't described, so that's why you can kind of make it to be an attribute of the order, or you can just say the number is your identity. Okay, so this kind of, we try to capture as many constraints as possible from the description. Relationship can have attributes. What relationship cannot have is that relationship cannot have identity. Now, the next thing that you may want to check is that is this ER diagram actually conform to real world? Is the constraints that we impose over here actually make sense on the real world? Well, we can try to take a look at what happens if we try to use this particular database. There is a kind of limitation on this ER diagram. See if you can spot it. But it has something to do with whether a customer can order the same book multiple times. Can a customer order the same book multiple times? Is this actually permitted? And the answer is yes, if the customer uses different credit cards. Okay, so there's that. Now, if we have credit card as an attribute instead, so let's say this is a second version. Let me use a different color. If instead of this, I have a credit card as an attribute of a customer, then this restriction is even worse, because a customer cannot even order the same book multiple times. Okay, so there are things that you may need to to consider further once you have your first draft of a ER diagram. Okay. So the question is, how would we answer this? How would we remove these restrictions fully? Well, there's one way. You may not like it. It's basically there's orders, there's books, there's customers, And to differentiate this, you can have another entity, time. When a customer orders the same book multiple times, we can almost be sure that they order it at different times. So this is one way to resolve this particular problem. Okay. If you make order an entity, so there's a command there. Why not make order an entity? If you make order an entity, it cannot relate customers and books. Okay, so that is probably an even stronger restrictions. But if you want to make order an entity, you can, but then how would you say that this particular customer buy this particular book? Because order is an entity, right? So there's that. Now, these are the basic ER concepts. What I want to show you are additional ER concepts. Some of this you have to use because it's part of the project restrictions. I believe weak entity sets, you have to have at least one. Now previously, we have never differentiated between the two, but this always caused a lot of confusions. Now I'm separating these two, and it is actually, at least I found one book that also uses this. So at least it's something that is more normal than it is. It's not my own inventions. But there are two kinds. One is identity dependency, and the other one is existential dependency. Okay. So what is identity dependency and what is existential dependency, and how do we differentiate them? The only difference between them is that an existential dependency can uniquely identify each of the entity. So if this one has an attribute A1, which is a primary key, given an A1, I can uniquely identify any entity within this weak entity sets. But if I have this A1 as a primary key, I cannot even uniquely identify an entity within this particular entity sets or weak entity sets. Okay, so how do we? What kind of real world problem that we can map into this? Okay. An identity dependency is something more like you have books has chapters. Okay. So books has chapters, but chapters, let's say for instance, you have chapter 1. A lot of books have chapter 1. So you do not know which book this chapter belongs to. Chapter 2, a lot of books have chapter 2. Okay, so even though you can make this to be your identity of the chapter, but because it is an identity dependency, then each one of this partial key, so it's basically not even a full identity, it's a partial identity. It cannot fully identify. So yeah, so to fully identify a particular chapter, you must know what book you are looking for. Okay, so let's say we take my book, CS2102, chapter 1. Now it's clear that we are talking about chapter 1 of my book. If I'm just telling you chapter 1, it can be other book. It can be the Ramakrishnan book. Okay, it can be other books. So a chapter is an identity dependency. It's a weak entity set that is involved in an identity dependency. But what about existential dependency? In the case of insurance, I have my own policy. I have my child policy. Okay. So I have an insurance policy, and my child has an insurance policy, which means that there's a policy number. I may also have a policy number. But my child policy number should uniquely identify my child's policy. Okay, it should be unique within the entire database. So this is an example of existential dependency. But my child cannot have a policy if I no longer has a policy. If I opt out of my insurance, my child cannot have insurance. Okay, so that's the difference between the identity dependency and existential dependency. And another kind of concepts is the is-a hierarchy. So this is another way to write it is a hierarchy. It's kind of talking about the superclass subclass relationship, where this is your superclass or the generalized one, this is your specialized one, which is the subclass. Okay, the implicit one is that if I have an attribute A1 over here, I don't need to have A1 over here, I just need to have A2 over here. There are two different constraints that you can have, and that's the overlap and the covering constraint. I just learned that there's a notation that you can use, but it's not really standard, but it's an additional notation. If you want to follow this, it's up to you, but I'm not using this for the assignment at all. So there are 4 sets of constraint. Does it satisfy overlap? So yes or no. Does it satisfy covering? Yes or no. Okay, so they can be yes, 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 no, no, yes, and no, no. We also have 4 kinds of arrows. This. Okay, you can imagine that, well, if it satisfies both overlap and covering, then it must be this arrow. If it doesn't even satisfy overlap and doesn't satisfy covering, sorry. Actually, I forget. I think this one, if you satisfy overlap but you don't satisfy covering, this one, I think. This one is the strongest one. You don't satisfy overlap and you satisfy covering. This is just covering. Oh, no, this is both overlap and covering, and this one is okay. There was this notation, but I forgot which one it is. The main thing is that I'm not using this. Okay, if you want to say overlap and covering, you have to specify that as an additional constraint. Okay. Then there's aggregation. In some cases, we want to say certain useful things. Things like, you have horse, you have people, and then there's ownership, right? Own. You do not want to talk about about all people. You don't want to talk about all horses. You only want to talk about people who owns horses. Okay? So let's say people who owns horses can be involved in a race. You want to say that only people who own horses can be involved in a race. So to do that, you need to kind of connect between the own here and the involved. But the own here is a relationship. You cannot do that directly. You have to make this to be an aggregate. Or it can be, you do not need to have. It can be any kind of arrow, so you can have this arrow. So this diagram says that only people who own a horse can be involved in a race. Right? There's a few questions here about the about the weak entity sets. NW can also have its own attributes. Yes, and this one can have its own attributes. So like chapters, you can say, you can have a book chapter. The chapter number should kind of partially identify which entity you want, but to fully identify the entity, you need to also look at the books. But it can have its own other attributes, like so if we're talking about, if this one is talking about chapter, the number can be a partial key, and then you can have a chapter name. It has its own attribute. There's another question. So when we say NW has an existential dependency, it's referring to a specific attribute in NW. No, it's talking about the entire NW. It's talking about the entire entity sets, the weak entity sets. Can a weak entity be fully identified using its own attribute? So here I was talking about insurance policy, and this one was a dependent policy. But a dependent policy should still have a policy number. Given a policy number, I can identify my child's policy. Okay. Now, this notation was actually something that I half invent, but actually there's someone else who invented, and that's Prof. Ling. If you look at other books or somewhere on the internet, typically what you find is something like you put a box around the entire thing. Okay, this can be confusing, okay? Because what these people usually do is that if this entire aggregate is involved in another relationship, it's still connected here. So this part is the one that is causing confusions. You should not even have this. So here, if you notice, on this part, there's no line. All right? So if you want to talk about the people who are only involved in the race, then yes, you need to make this to be a box. Then this can be involved in another relationship. Okay, so that's basically that. Okay, now the last part is to convert from ER to SQL. If you have entity sets, then it's actually pretty easy. Just look at the identity attributes, make that to be a primary key. Everything else is for this two, is a non-primary key. Whether you want to make this null or not null, it's up to you. It's not necessarily be captured here if you want. But typically, we say that it's always non-null. Okay. For a relationship, for unconstrained relationship, then the primary key is just the primary key of the entities that are involved. Okay. So if it has additional attributes like this, grade. You put that as an additional column. If you have a key constraint, there are two approaches that you can use. This one assumes, the approach one assumes that profs and students are already defined. Okay? They are already created as a separate entity. If you have that, then you just have, the main difference is that the primary key will just have to be SID. Okay? Because the student basically can be involved at most once. Now, of course, this one, I make a little bit of mistake here. This one should be not null. I'm going to modify this later. So this one should be not null. There should be a not null constraint over there. Now, the other approach is that this one exists. This one doesn't exist. You combine this into one table. Okay, and that we call that as supervised students. Okay, so the main thing is not that this is correct. The main thing is, how do you know that this is correct? Okay, if you want to have a student that is not supervised by any professors, we can have that in the combined table like this. The value of the PID can be set to null. So that's the difference. In this one, it should be not null. In this one, it should be, in the second approach, because we merge supervisors and students, we allow this to be null. Okay? And if this is null, that means this particular student is not supervised at all. For key and total participation, the only way to convert this is to merge. So this one you merge. So the student does not exist, the prof exists, but you do not allow this to be null. Okay. Now it is impossible to have a student like the 1434C that we have before that exists with a null. This one is not allowed now, which means that this one is not allowed. Okay? So by merging these two tables, you have created both the supervisors table and the students table. Oh, right. Right. Again, this one should not be there. Oops. This one also should not be there. Okay, so those are not supposed to be there. Okay, now for the roles, to differentiate between the roles, what we need to do is just basically the roles is set to be the columns. So the student table must exist. This is the mentors table. They just references the student table twice, but you differentiate the attribute names. Okay, that's the difference. Now, here is a concrete difference between an identity dependency and an existential dependency. In an identity dependency, here we assume that this one exists. We have to merge these two. Okay, because again, the reason why we merge these two is because of this arrow over here. This arrow requires us to merge these two tables. And what we need to do is we need to put the ID of this. So this is an ID. This is an attribute. We need to put this as part of the primary key. So not just this. We say that the NWID is an identity of NW, but it is not a full identity because it's an identity dependency relationship. So we have to put both as our primary key. The other thing that you need to note is that there's this on-delete cascade, because the entity, this particular weak entity, cannot exist if you remove the entity that you refer to. So this is the strong entity. If you remove the strong entity, the weak entity has to also be removed. So that's why you have an on-delete cascade. Now, the main difference between the identity dependency and an existential dependency is that the primary key for the existential dependency is just this. The identity of the weak entity can fully, uniquely identify that particular weak entity. Okay. So this is what we have. Okay, so that is the main difference. There's a question: can the strong entity be on its own? Yes, we say that this strong entity exists. There's a table called ent, so that's what we assume. Also for this, there's a table called ent, which is implied by this. Oh, again, this one is ent. Okay, that's the main difference between the existential and identity dependency. For an is-a relationship, there are multiple ways to do this. The first approach is if you do not have covering constraint. We already have a student table, so we just references those. Okay, the primary key is still the primary key over here. Actually, you don't even need this. And yeah, there's still on-delete cascade. Okay, the other attributes can be added as well. Okay, now, if you already have, so this one is with. If you have a covering constraint, then you do not need to have the students table. On this second approach, no students table. Okay, I do not need to reference this, but what I need to do is this particular attributes need to also be included over here, as you can see over here. Okay, because with covering, that means a student must be either an undergrad or a grad, so you have just insert it there directly rather than inserting it here. For aggregation, the idea is simple. We assume that there's already this particular table, there's already this particular table, there's already this particular table. What we have then, for the relation A table, is basically constructed as per normal, referencing this, referencing this. It is then used as if, okay, so this one, it is used as if it is an entity set. All right. So there's that, right? So that's how it is. So you have the relation A over here being referenced, which means that you treat relation A as if it is an entity. That's basically the difference. Okay, so we don't really have time for this because I wanted to show you how to convert this, but I'm just going to update the notes, the lecture notes. So we are going to, I'm going to update these notes to show you what would be kind of the SQL create table for this. Okay, so you just wait for the lecture notes, and yes, I'll be uploading the annotated version. So I have been doing that, I believe. Hopefully I did not forget that last week. So yeah, so that's it for the lecture. So let me start answering the questions. So if you want to go for another lecture, feel free to leave. So yeah, so let me start answering questions over here. I think that this is one that I have not answered. For the earlier example, user has password, is that considered weak entity set? So it is the password should not even be considered an entity in the first place. Okay? Because your ER diagram, even though it's just a conceptual abstract thing, it should capture a real world constraint. So the question is, can you even have a password existing? Okay. If you cannot have, and you said there is an existential dependency, then will you be able to uniquely identify? So if you say that it's identity dependency, but there can then you can also ask yourself, can a user has multiple password? Because remember, in my password example, which is a long way back, in my password example, the one that has a key and total participation is the user. User can only have one password. So it does not make sense that the password is the one that is a weak entity. It should be the user that is a weak entity. But does it even make sense to have a user to be a weak entity? Right? So in this case, the idea is that password should not even be an entity. Okay. So be careful with the weak entity, because the arrow on the weak entity here, the key and total participation constraint is from the weak entity to the relationship, not the other way around. Right, so then just to confirm, we are not going to use additional concepts. If you're talking about the covering and overlap, I'm not going to use the arrows for this. But if you have it, if you have these restrictions, if you have these constraints on your ER diagram, just mention it. Or if you want, you can use the arrows. I will add the notes with the correct arrows. If you want to use it, feel free to use it. But when I'm giving questions, I will not be using those arrows. Okay, that's my guarantee to you. The assignment is actually already available. Is there? Let me add the file. It should be this one. Yeah, so there's this. If you want to look at it first, you can try to attempt this here without going to cosmology first. Okay, so more questions. What's your keyboard and drawing tablet? Oh, that's actually Logitech. Is it too loud? Keyboard and mouse. Logitech. It's very, very good. I will recommend Logitech. Tablet is the usual one. Welcome. There's a under key constraint. What is the purpose of attribute names? Name is the student's name. This one is the student's name. Okay, so why do we have this? Because we combine this, right? We merge this. So all the entities, all the attributes of the students have to be within this table. Okay. Why primary key cannot be an attribute of a relation? No, so what I'm saying is that a relationship cannot have its own set of identity. Okay. Here's the thing, right? You should. This second part is an excellent question. You're right. You're totally correct. Using the book example, if I have the transaction numbers to track each order, then creating a separate entity seems redundant. But you need to separate the logical part of it, which is the ER diagram, and your actual. Then you need to differentiate between your logical view, like this, and your actual table. Now, in your actual table, because let's say you have a tracking ID, let's say you have a tracking ID, what you will have is basically you're going to have a create table track order, which merge between your tracking and your order. This allows you to have have a customer order multiple books at the same time, okay? Because you have a tracking ID. Like PID, you have a CID, you have a ISBN. Let's just make things easy. In the end, if you want to merge this, it's fine. It's just that logically speaking, the ER diagram should be something like this, except that this one is a tracking. This is the logical view of your ER diagram. The implementation can merge. It's fine. And even if you want to make such that this one is the only primary key, it's also fine. Which means that your ER diagram will basically looks like this. Okay? This means that you basically want the reason why this is needed is because you want to make sure that the customer can order multiple books. In the end, what will happen is that the order and the track will be merged. Okay, so that's the deadline for assignment 1 is week 6. Yes. Okay, there's a question. How does the on cascade works? Well, on cascade, basically, if I have a table, which says A, B, and let's say just for ABA like this, right? So let's say this A let me try to think about an example. A, B, C. Okay, let's say this one is null. Let's say this one refers to A, this one refers to B. So this particular attributes will refer to this particular attributes from a different row. So this one refers to this one refers to this, but they are on the same table. Okay, if you erase this, on delete cascade will just remove this because whatever you are referencing has been gone. So you remove this, and now this one, whatever you're referencing is gone, so you remove this. That's what on delete cascade is. Key constraint. No, this one is not. It's not all. Okay. It says if at one participate, then it must participate in at most one. Or yeah, I mean it depends on how you read this, because in at most one that means it can be 0, right? So all entities may not even participate. So may or may not participate. If participate, at most one. That's what key constraint is. While we are at this, might as well say total participation. Must participate can be more than one. Okay, so another way you can look at this is that this one is between 0. This is the number of participation is between 0 and 1. This one, the number of participation is greater than or equals to 1. If you combine, you must satisfy both, which means that it can be P equals to 1. It must participate, and it must participate exactly once. Covering and overlap. Overlap means that, let me delete overlap. So using the example of the undergrad, so I have students. Either it's a U grad or a grad. Overlap means I can have a student that is both undergrad and graduate student. So I can have a, let's say, a student A who is doing both Bachelor of Computing and, let's say, MBA. Okay. If I allow a student to do this, then it satisfies overlap constraint. Now, if on the other hand, I don't allow this, I don't allow people who are doing a bachelor doing a master degree, then it does not satisfy overlap constraint. For the covering, means that every student must be either undergrad or graduate. If I allow A to be other kind of student, let's say just part-time, which is not captured over here, then that means it does not satisfy covering constraint. But if I don't allow any kind, the student must be either undergrad or grad, and only these two, it cannot be anything else, then it satisfies covering constraint. Okay, so that's the constraint. how do you key or and and condition in SQL? It's just select from where something I believe this or binds more tightly, I think. In any case, there always be a source of confusion. So if you are not sure, then just always put a bracket. If this is what you mean, then just use brackets. Okay. Why do we combine tables? Well, part of the reason why we combine tables is because it's simpler and it still works. Okay, so think about it. This one, either we separate or we combine. Doesn't really matter. If we combine, we have one fewer table. Makes our lives easier. Okay, so the reason why we want to combine is because sometimes it makes our lives easier. On the other hand, sometimes like this, if you don't combine at all, so this one is something. For this one, if you don't combine at all, for this, if not combined, then the total participation constraint is not enforced. Okay, so for key plus total participation constraint, you have to make it to be a combined table. Otherwise, the total participation constraint is not enforced. Existential dependency. Okay. The end ID is not referencing itself. This is referencing the end table. We are creating this table, the EX and W. So we are creating this table. It's not referencing itself. It is referencing this table. Okay. So yeah. Whether the PID can be null in the supervised key. Here, I explicitly put not null. You cannot be null because if you allow it to be null, it kind of indicates that the student is not, does not have a supervisor. So no, it cannot be null. Can you quickly go through the is a covering? The covering constraint basically says that a student must be either an undergrad or a grad. It can be both, but it must be one of them. You cannot have any other kinds of students. You cannot have a part-time students. You cannot have a I don't know, PhD students maybe, or maybe that's part of the grade. But you cannot have other kinds of students. Okay. So that's what the covering constraint says. how to key is null and not null in SQL query. Select from where X is null or is not null. This is how you code. Okay. Good. Any other questions? So yeah, so I think there's been a lot of requests. I'll try to put the archipelago questions into the cosmology, but the main thing about archipelago is that I need to know what you know. So the reason why we are using it is because I need to know what you know. Because if I don't know what you know, or I don't know what you don't know, then it'll be hard for me to pace the lecture also and the assignments. Okay, so unfortunately, we will have to deal with archipelago again. But hopefully you are more comfortable with it. Actually, I forgot what's written in the book. But if N1 can participate in rel multiple times, it means that the key constraint is not. If the answer is no, it should be, if the answer is no, then there should be a key constraint. If the answer is yes, then there's no key constraint. That should be how it is. I'm not sure whether I wrote it correctly or not. Let me bring up the book. Example 412. Yeah, I think it should be, if the answer is no, then it's a key constraint. I think that's kind of a leap in concepts there. You're right. I'll try to make it clearer in the book. So there's another question. Key constraints can have null. Yeah, the PID can be null. Because a prof need not exist. A student may not have a prof that is supervising. So it allows null. Yes. So this one should be, yeah, this one is correct. It allows null. But for this one, if you are using this, then it should be not null for approach 1. Okay. So any other questions? You need to differentiate between the null and the meaning of the null. Here, because we combine the table, we combine the table like this. The value of null over here means that a student does not have a professor. Right? It's a different thing. This is the implementation. This is the implementation. This is the logical view. Okay, in the logical view, what do you mean by you say can it have null? Because I don't have null at all. It is a logical view. There's no such thing as null within this logical view. In the implementation, then yes, there is null. And that null, this particular null, means that a particular student does not have a professor. And that is because in our implementation, we combine the two tables. The ER diagrams remains the same. The implementation is different. If you are using this, then there's no null, right? Because this one is not null. So that should answer your question. Then yeah, it should not be null. But whether or not we allow null in the actual table depends on which approach we are using. So if you're using this, well, if you're using this, if there's an entry in the supervisors table, then the prof cannot be null. For this one, there's not even a supervisors table. There's no entry on the supervisors table. Conceptually, we don't have a supervisor, but we have an entry. If you want to look, if you're given this implementation and you want to say, give me an entry on the supervisors table, it means all you have to do is look at the supervised students table and filter out everything that the PID is null. That content is the content of the supervisors relationship set. Okay, you need to differentiate between the logical view and the actual implementation. In the logical view, an entry over here may not an entry in here may not correspond to an actual implementation. It can be a subset of that implementation. And so if you look at here, the way I mention it is the entries in the relationship set. I do not say it is an entry on the table because I don't care about the table. There can be null on the table, but on the relationship set, there cannot be null. Okay? There is a totally different viewpoint over here. So you need to be very, very careful with this. This is a logical view. The underlying implementation can be a combined table. Parts of this table, once you filter out all the unnecessary information, gives you exactly the entries on the supervisor's relationship set. Okay. So yeah, so it's just that. There's no null on the ER diagram, especially not on the relationship set. There's no null. But on the implementation, on the actual table, there can be null. Okay, so let me answer another question. There won't be one-to-many, many-to-one. I won't be using that terminology because again, it's quite confusing, right? And if I talk about ternary, what will you say? One, many, one, many, one. So we will talk about whether there's a key constraint, whether there's a total participation constraint. So that's what we're going to talk about. If you want to use the terminology, you can. But what I want to do is I want to make it precise that whether we have a key constraint, whether we have a total participation constraint or not. because sometimes saying that there's a one-to-one relationship can be kind of ambiguous. So I'll try to avoid that. All right. So any other questions? So if there's no more questions, then let me end the stream. I'll try to look at the live chat again and see if there are any unanswered questions, and I will try to answer that in the lecture notes itself. But for the last part here, yeah, I'm just going to add into the notes what will be the SQL code related to this. Okay, so good luck for your projects and good luck for your assignments.